and plus music a little bit, and everybody else. He writes all their songs. Yes, he writes all his own music, and for everybody else in there, young
No,
music.
actually, no. However you should have no material.
Couldn't find material. He doesn't write like he doesn't have no. He doesn't have anything.
Okay, no. Sorry.
In a little setting.
Boys in-ground pool. Stayed on the grassy. He's a rapper.
How can I put it in there? You can still be from the put in your grandparents' house.
We have the public pool.
But I'm just my grandmother had to do it, but I wouldn't consider it like my grandmother was I wasn't like
So, I mean,
I'm not saying it was. I looked at that food, I used to always get
I'm just saying.
Okay, let's get started. So, part of your homework was to finish this chart. You can just hold on to it for yourself. Okay? I'm going to talk. Let's first talk about this situation here, the middle row. Okay, the middle row, where the first derivative is 0. So, apart from the graph of the function, if the first derivative is 0, what does that mean about? What can you say about the accumulation if you have the first derivative is 0? So what could we just conclude in general if the first derivative is 0? What's that? So we could have a constant function, all right? So the accumulation itself could just be constant, right? And so, of course, everywhere then the first derivative would be 0. But what about if it's not a constant function? If the accumulation is changing as x changes, and we find a local area or local point where the first derivative is 0. Talia.
You're going from negative to positive, positive to negative.
What's negative or what's positive?
The rate of accumulation is changing. It's either going from negative to positive, positive to negative.
Okay, so the rate is changing from negative to positive or positive to negative. Is that true? Dan.
I was just going to say, there's no accumulation happening.
Okay, so right at that point, if first derivative is 0, then no accumulation is occurring, or there's no change in the accumulated amount. Okay, what were we going to say, Elijah?
That it's neither accumulating in positive or negative terms.
Okay, so does the accumulation, does it either switch from increasing to decreasing or decreasing to increasing? Or is there something else that could happen?
Well, it could go from increasing to increasing and decreasing to decreasing.
How? It's increasing, and then when it's 0, or when the derivative is 0, the accumulation is
It's just kind of flattened out, right?
pausing for a moment, and then could keep increasing, right? So this is the idea of a critical value. Okay, a critical value is any place where the first derivative is 0. So what is definitely true is that the accumulation pauses for that moment. It's not increasing or decreasing for just that moment. It's staying constant. Okay, so f prime of c tells us that f stops or pauses momentarily increasing or decreasing at c. That we know for sure. Like Corey was saying, f might continue to decrease, or it might continue to increase, or it might change from increasing to decreasing or decreasing to increasing. So what happens if it changes? Say if accumulation changes from increasing, and then there's that pause where the derivative is 0, and then it's decreasing, then what do we have? So in terms of the accumulation, what do we have? So it's increasing, and then it pauses, and then it's decreasing. So what can we say about the accumulation at that place of the pause? It's a maximum, right? Or like in a relative maximum, relative to the local area. Okay? But is that guaranteed? So going back to your so you should have we talked about last time like this, right? So right there, what happens? The accumulation pauses at the low point. It's decreasing, and then the accumulation pauses, and then it's increasing. When that happens, you have what's called a relative minimum. Okay, here? Yeah, so there's a moment right there at the very top where the first derivative is 0. We have a pause in the accumulation. It's not increasing nor decreasing. But if it changes from increasing to decreasing, then it's a maximum. Okay, so what about x cubed? You know what x cubed looks like? Yeah. So it comes in like this. It doesn't dip down. It pauses, but then it keeps going up. So it's going up, and then for just one moment there at 0, it pauses, and then it keeps going up. Is the first derivative 0 there? Do you have a maximum or a minimum? No. It's increasing, then it pauses, then it keeps increasing, so you don't have a max or a min. So just saying that the first derivative is 0, there's lots of different scenarios that could happen. But what we know for sure is that the accumulation pauses or stops for a moment. But beyond that, we're seeing that there's different things. So we want to kind of narrow it down because we want to find these key places, say, of relative maximum or relative minimum. Okay, so here's this x cubed. So the first derivative is 0, but it's not a relative max or min. So if you have a relative max or min, this is true. You have a pause. But saying that the first derivative is 0 doesn't guarantee a max or min. That's what we're saying. Does it make sense? So what condition guarantees a max or min? So we need to get another condition, so a combination of information so that we can definitively say, okay, we've got a relative max or we've got a relative min. So here's a situation where can you see a relative min and can you see a relative max in this graph? Okay? So at 0.42, first derivative is 0. At 1.58, first derivative is 0. Okay? So we have a relative max at 0.42, a relative min at 1.58. So what is this first one? What would be a condition that would guarantee that would be a relative max at 0.42? What can you think of? What'd you say?
The second derivative should be negative.
She wants the second derivative to be negative. What would that mean, the second derivative being negative? What would that tell us? But talk about accumulation. That's true. That's true. But what if the second derivative is negative? What does it mean for the accumulation?
It means the accumulation would decrease to the point of like decreasing the function.
Okay? It means a decreasing accumulation. A decreasing. I'm sorry. Say it again. What'd you say?
Yeah. Well, so like the actual accumulation is decreasing.
If the second derivative is negative, does the accumulation have to be?
Assuming the rate is decreasing.
Rate is decreasing,
That's
right?
the first
So is the rate decreasing all through there? Yeah, so the rate is decreasing, it's becoming less positive or more negative. So the rate's decreasing, and that would allow us to know that if we also had the first derivative to be 0, if it paused for a moment, then it'll have to be a maximum. So if the rate's decreasing, and your accumulation pauses, you get a max. And what is that? That's the second derivative is negative and the first derivative is 0. Okay? Another way, so second derivative, but another way you can talk about is the first derivative, right? What's the first derivative to the left of that 0? Positive, right? And what's the first derivative over here? Negative. So that's another way you could check to see if you hit a local max. If the first derivative changed from positive to negative, so first derivative positive, then 0, then negative, that would be another way to say you have a local max. Okay. Okay. Does this make sense? Second derivative greater than 0 means the first derivative is, tell the person next to you. Second derivative greater than 0 means the first derivative is what, and what would it mean in our function? Go, tell the person next to you.
Agreed.
Second derivative is greater than 0. The second derivative is greater than 0. What does that mean for the first derivative? What applies here? Okay, Chunzi, do you know what this answer is? Second derivative is positive, then the first derivative is? She wants the rate to be increasing. Stanley, do you agree with that? The second derivative is positive, and the first derivative is increasing.
Yeah.
Jacob, you like it? Okay, so what applies? So what in this scenario applies to that statement? The second derivative greater than 0 means the first derivative is increasing. No, I guess that kind of gives away the answer, doesn't it? So is the first derivative increasing all through there? Yeah, because it's becoming less negative and more positive. The rate is. Okay. Second derivative less than 0 means first derivative is decreasing. And that happens where? At our relative maximum. Okay, so here's a practice problem. Consider this is an accumulation function called g. G of x is this function. So at the given x values here, I want you to find the current value of the accumulation and find appropriate values to determine how the accumulation is changing and express your conclusions with words. Okay? This is totally a numerical exercise, no graphs. So just numerically, we're analyzing what's happening at each of these x values. What's the accumulation? And everything you can find out about how the accumulation is changing. Okay? So I'm kind of leaving it open-ended for you to think about it and figure some things out on your own. Okay, you can work together. So take 5 or 10 minutes to work on this. Okay?
So you just
Okay. Write down the function, write down the x values. I need to look for something else in my computer. So have this and jot down just so you know exactly what your goal is here. So jot the function down, the x values. Do them in this order as well. Do them in this order as well.
And then you can find the rate of change of the
Zero.
Okay, 10 seconds. I'm taking it down.
You're taking the second derivative, you take the first derivative. So like I went from this to find the first, that's 12x squared minus 6x. And then we're just
Okay. Everyone got it down? Keep working on it. Not happy. Megan, tell me about x equals 0. What'd you find out? So how can we express that? G of? What does that mean?
It means that at when x is 0, y is 5.
Okay. So when x is 0, and what's y mean here? Megan. Amount of accumulation. Okay, what else did you find about x equals 0? Okay, you're talking about the 3? Yeah, the 3 is positive, that's true. But we had other stuff to do here, so like how is the accumulation changing at 0? Did you find that out?
The accumulation at 0,
Uh-huh.
it's increasing.
How do you know that?
Because after you go to 0.5, it increases.
Okay, so you went on and found another accumulation and compared them.
Yeah.
But just because it's higher at 0.5, does it mean it's increasing at 0? It could do lots of different things in between there, right? Yeah, it could go up and down 10 times between 0 and 0.5. So we want to confidently assert what's happening. How is it the accumulation changing at 0? Lauren?
Would it be increasing because the accumulation at 0 is a positive number?
Okay, so if the accumulation is positive, then the accumulation is increasing. Is it true? Well, I mean, think about it. If the accumulation is at a current value of 3, and that's a positive value, does that mean it's increasing? And if the current value of the accumulation was negative 2, would that mean it's decreasing? No, not necessarily, right? So, what kind of tools do we have to figure out how it's changing? Yeah.
You do the
First derivative, okay.
Change in x, and then you plug in 0, you get a negative number.
All right, so what is that? Let's write this down so we don't do it a million times. What is it?
4x cubed.
4x cubed.
Minus 18x squared.
Okay, so this is the rate of change, and you want to plug in, Marcus?
0.
And Sharon, what does that give us? And what does that mean?
That the rate of that the accumulation is
She wants the accumulation is decreasing at 0. Can we do any better than that?
Yes.
Beth, how can we do even better than that? Second derivative? Remember this notation? This is a common notation. Okay? Tell me.
12x squared minus 36x plus 25.
Okay? And what did you find?
At 0, it's 1.
The second derivative at 0 is? And what does that tell us about how the accumulation is changing? What's that?
Well, it was decreasing, so it increased.
So it's decreasing and increasing at 0. Is it decreasing or increasing the accumulation? What? Did you? The accumulation is decreasing. But the rate at which it's decreasing is increasing.
Because the first derivative is the accumulation and the second one is the rate, so it was decreasing.
Okay, be careful. The first derivative is not the accumulation. It's how can you? I mean, you're thinking the right thing. You just got to state it correctly. The first derivative is about. That's right. The rate at which it's accumulating, and the second derivative is about.
The rate of change at which is
I know what it is. I just don't want to say it though.
So how do you say it, Tyler?
the rate at which the rate of change is changing.
The rate at which the rate is changing. Okay, or yeah, it's just a number that's telling us how the rate is changing. It tells us how the rate is changing. Okay, so in that local area at 0, what is the shape of the graph? So going up or down? Going down. And how is it going down? Most people are saying this. Is that right? Yeah. And that's our negative first derivative, positive second derivative means that the accumulation is decreasing, but that rate is becoming less negative. So it's increasing. The rate is increasing. Okay, how about 0.5? Lauren in the back, how'd 0.5 go? You tell me anything? Okay, Richard. Nothing at all about x equals 0.5. Jacob.
The rate of accumulation is 0.
And which of these apply? Which are you talking about here?
Oh, G5.
The first derivative?
Yeah.
You said was? 0. Therefore, what can you conclude about?
It's reaching, well, it might be reaching a maximum.
It might be reaching a maximum or a minimum, but what can you say for sure?
It's changing values from negative to positive to negative.
Okay, so first of all, what is negative or positive, and second of all, is that guaranteed? What can we say for sure from this statement right here? What's that? The rate is not changing. No, the rate could be changing. What? Right. What were you going to say?
Well, I was gonna say, can we talk about like increasing from 0 to 0.5? Like,
No, because there could be
is this
lots of different things happen in between there.
Oh,
You see? So the rate, it could swing from positive to negative to 0 10 times in between 0 and 0.5. So we're just focusing on at 0.5. And so, what did you say? The accumulation isn't changing. Agree with that? For a moment, the accumulation pauses. It's not increasing or decreasing for a moment. What'd you get for the amount of accumulation? 1.3, okay. So, does that kind of match up? So we can generally kind of say, look, so would we say the accumulation was decreasing, and now from at 0.5 it's less. Again, we're not sure exactly what's happening in between, but it looks like, okay, here the accumulation's going down, and it went down from 3 to 1.3. You see? Okay, what about the second derivative? Did you find the second derivative here? How about Adelaide?
I got the second derivative from 9.
Someone else get that?
Yeah.
So, conclusion about how the accumulation is changing at, or what's happening at x equals 0.5. Okay? He wants there to be a max. Zoo, you agree with that? Relative maximum at 0.5. You say yes? Judith, tell me. Why?
chart. I know that's cheating, but I don't really know.
Well, what does this tell us about the accumulation?
It's not changing.
Pausing for a moment. And what does this tell us about the accumulation?
That it's increasing.
What's increasing? The rate is increasing. Connor, so?
Oh, it's concave up.
Okay. Yeah, so if it's pausing and the rate is increasing, the accumulation is pausing and the rate is increasing, what's that scenario? Isn't that what happens right there? Here's our rate is increasing all through there. Our rate is increasing. That's positive second derivative. And the accumulation is pausing. So that has to be local or relative minimum. Okay, let's skip down to x equals 1. Christina, tell me. Did you get anything for...
When the rate of the accumulation function will be 2.
So you got the rate was 2?
I mean, no. For the derivative one, it will be, yeah, 2. Okay.
So the rate of change at x equals 1 is 2.
Yes.
What does it mean?
That it's positive increasing.
What's increasing?
The rate,
The rate is increasing.
yeah.
Stanley,
Accumulation is increasing.
the accumulation is increasing. Which is it? Yeah, 2 is the rate of change. It's a positive rate of change. That means the accumulation is increasing. What about the second derivative? Connor, what does it mean? Okay, he said there's no change in the rate of change, but also our rate of change is positive, so we're increasing and there's no change in the rate. So the accumulation is going up, staying steady, or going down, first of all? Going up. And that there's no change in the rate. How is it going up? Yeah, like at a constant rate momentarily. At a constant rate momentarily. So we didn't really talk about this. There's 2 ways that could happen. The rate could be decreasing, and then the rate could be increasing. Or the rate could be increasing, and then the rate pauses, and then the rate decreases. Okay, either case is called, this is called an inflection point. So an inflection point is where the rate changes from either decreasing to increasing, or the rate changes from increasing to decreasing. And so at that place of where the rate changes, your second derivative will be 0. Okay, yeah, so in your chart, where's this in your chart? Top middle, top middle. So the key is that the function is increasing. It's going up. It's going up. It doesn't pause. But it's the way the rate changes pauses. Okay, so the rate pauses, but the function's going up. The accumulation is going up. Okay, how about at x equals 2? David, did you make any progress on that? So you got the first derivative was 0? You got them both to be 0. So let's talk about what this means. So if the first derivative is 0, Chelsea, what does that mean? Just if the first derivative is 0. What does that tell us about the accumulation? What's that? It's not changing, that's right. So it pauses for a moment. The accumulation pauses. It's not going up or going down, just for a moment. Okay? Second derivative is 0. Means?
The rate at which it's changing is from zero to zero.
Yeah, so good. The rate at which it's changing also pauses for a moment. Okay, so we're going to be flattened. The accumulations is flattened out. It's not changing, and then also the rate is kind of constant for a moment, right? Not changing also. So what could that look like? All right, if it's not a line, what could it look like? It's going to be an inflection point, but what will be different about it, say, than this?
Well, like this, I feel like it came through the rate of change after the point 0.
And how will that be different?
Like there will be a portion which looks like it's almost horizontal.
It'll flatten out, right? Instead of still going up as it's inflecting, it'll flatten out for a moment. So it could be like this. It could be like, or it could be like this. So it's an inflection point, but it's also no change in the accumulation. So for a momentary pause. Okay, any questions on, so we didn't do them all, we skipped 1.5 and 3, but any questions on this exercise practicing? Yeah, Jacob.
Is it possible for the second derivative to be a positive value and the first derivative to be 0? So,
Yeah, we had it right here. Let's see, positive. Yeah, we had it right here. So what would that mean? Was that your question?
yeah.
Okay. So you can have one be 0 and the other not be 0. They're both legitimate. They're both legitimate. Okay. Other questions?
What happens when, like for 1.5, the second derivative is a negative number?
Okay. So what'd you get for those?
1 and negative 3.
So this one was 1
Yes.
and this was negative 3. Okay, you tell me. So what's happening to the accumulation if the first derivative is 1? Accumulation's going up. You don't know if it's positive or negative, right? You just know that if you change x a little bit, you get a positive change in y. So we're going up. What does that tell you? The second derivative is negative. It means that the rate is decreasing. So how can something be accumulating positive, but the rate is decreasing? What would that look like?
A little bit less.
Well, yes. Well, don't go too far. You keep going like this. Was it?
I was just saying like accumulating a little bit less, so it's
Yeah, so draw it with your finger. What would that be?
just
Right.
gradually.
That's right. Yeah, so this scenario would be, it's going up, but it's going up at a decreasing rate. So what quadrant, or what in your table, what is that?
Top right.
Is it top right? Top right. Make sense? Yes, Lauren?
It could be a question, but the top one, the reason it's concave up
Okay.
is because the rate is becoming less negative.
And right. So we know the rate is negative, so it's got to be going down.
Yeah.
This says that the rate is doing what? Increasing. So if the rate is negative and increasing, it's becoming less negative.
So less of a downward, it's going.
Right. So this is a steep negative rate, then less of a negative rate, then less of a negative rate, and that's an increasing rate, and therefore concave up. All good questions. Anything else on this one, on this page? Okay, so now let's try it the other way. So here's a function. So now to determine numerically if j has, and I'm not going to give you the x values, now you're going to go find any possible relative maxes or mins, or inflection points. So what would it take to determine numerically relative maxes or mins? So then for each that you find, explain your reasoning, and include all the associated values that help you to form your conclusions. Okay, go.
So find a zero, so it would be quadratic equation.
Don't talk about it.
This is A, that's C.
It's 2A, all over 2A.
Sure.
Right?
Yeah. Raise the second power. Yeah, we do the derivative. We're looking for where the derivative is. Yeah, we're looking for where the derivative is zero.
Okay, somebody tell me what it is.
This isn't about guessing, okay? This isn't about just throwing x values and guessing. So it's like how can we, without making guesses, pinpoint exactly what these x values are?
Or, I mean, if you make that equal to
3 is A, 18 is B,
but you also
the rate is 0 or
you also
Find out original. Okay, so we would find the value of the double prime at those two values.
so I
2 minus 5 and 5 and 5.
so now I plug both of these into this. 4 is 6, 18 minus 6 is 1. What does that mean? If it comes out 12, what does that mean?
That means you have a concave
So if it's 0 out 1, that means the first derivative.
second derivative was no. Next one.
No, I did 1 first.
Oh.
18 minus 6 is 12.
Okay. Second derivative.
X 1. Yeah? 30, so it's negative.
It's negative.
Yeah, 18 minus 30.
Okay, so I'm sure you guessed that finding the first and second derivatives is going to be important here, so I just wrote those down. So if we're trying to find relative maxes or mins, what are we going to do with this? Andrew? Okay, he wants to set the first derivative equal to 0. Is that right? Because relative maxes or mins occur where? First derivative, where we get a pause, right? At maximum we get a pause, or at the minimum we get a pause, okay? So, what happened when you did that? How in the world are we going to figure out this? So we're trying to look for the x values that make this true now, that make our first derivative equal to 0?
Factor out of 3.
Let's get a 3 out of there first. Or how about negative 3? So it'd be x squared minus 6x plus 5. Hopefully we got this.
X minus 1, X minus 6.
So I got x equals 1 and x equals 5. So therefore, at one of these there's a relative max, and at one of these there's a relative min. Is it right?
We don't know. Could be.
Adonijah says we don't know. David? Yeah, remember we got other situations besides relative max or min where the first derivative is 0. So this is not enough. This is not enough. We need more. So how can we figure out what's going on at x equals 1 numerically? Connor? Find out what the value of the second derivative is at x equals 1. What is it? So the second derivative at 1 is 12. Therefore, what's happening at 1? So we've got a pause in the accumulation, and the rate is increasing. How is that possible? It's like this, right? Rate's increasing, and we get a pause at the bottom. So, relative min at x equals 1. Same thing when you plug 5 in. What do you get? So at x equals 5? Because? Because the rate is decreasing. Okay? And then what about any inflection points?
I don't think we got that.
How inflection points happen where?
Double prime equals 0. So
Yeah, where the rate changes from increasing to decreasing or decreasing to increasing. And that's where the second derivative is 0. And so x equals?
3.
So you have an inflection point at x equals 3.
So when 18 minus 6x equals 0. Okay, gotcha.
Okay, quiz and recitation today. Relative or related rates and basic stuff about this that we covered before. Hi.
Can I just remind you that I'm going to be taking the
Yeah,
mastery
yeah.
test because you haven't given it to me yet.
Yep.
So just to make
Thanks.
sure. Okay.
I'm going to go get it right now.
Because our